Okay, guys. Hi, everyone. Thanks for coming to the seminar class today. So I'm Minesh Patel. I'm one of Professor Mutlu's PhD students, and I'll be handling lecture today. And so I've divided it into two separate pieces. So first, I'll continue the memory channel partitioning lecture that Professor Mutlu was teaching at the end. And so he had time to go over the technical content, but didn't actually make it to the analysis. So I'll give a brief recap of that paper, and then we'll do some analysis. And then I'll present one more example review for you guys. And hopefully you can use that as a baseline for when you're designing your own presentations and just get to see more examples. So I guess next week we're going to start with you guys presenting. So before I jump right into it, do you guys have any questions about course logistics or the presentation order or anything like this?
You're echoing a little bit.
I'm echoing? Yeah, I can lower the volume, I guess. Is that a little bit better? Or is that still echoey? I don't know. Seem fine?
I'd make it a little louder even, but
Okay.
I have a question about the synthesis report that we have to write at the very end.
Right.
You said there'd be a sample synthesis report, which you could look at. Because I don't know what we have to write there. Do we have to take notes during all of the presentations, or how does that work precisely? What do we have to put in there?
Okay, that's a good question.
So, taking notes about the presentations can be good for your reference, for sure, because some of the questions that you will have to answer in the synthesis report are, for example, what was your favorite paper, or how would you classify the different papers that were presented by the rest of the students. The presentations are going to be, or your presentations are going to be uploaded in the website as well, so you can always go and take a look at them again.
Okay.
It's always useful, but in general, in the synthesis report, what you will have to do is answering some questions.
Okay.
Questions that you will ask.
But general questions about different presentations, or specific questions?
Specific questions about
About
the seminar, and about like asking you what was your favorite paper, how would you rank like your favorite 4 papers, or things like that. I don't know, Mohammed. Is the synthesis report available in the previous
I think
website?
it's already uploaded online. This is a sample one, it's not uploaded.
Okay.
So just for your reference.
Okay.
Okay, yeah, sounds good. So I guess I'll get started with going through the memory channel partitioning lecture. So this is the paper we were reviewing last time. It's called Reducing Memory Interference in Multi-Core Systems via Application-Aware Memory Channel Partitioning. And this was co-authored by Professor Mutlu. Right, so I'm going to start off with a brief paper recap for those of us who don't remember, and just to refresh the paper. So the problem that this paper was trying to attack is the problem of inter-application interference. Right, so here we have a diagram of what a typical system might look like, and we have 2 cores, the red core and the blue core, and they're connected to a single memory controller, and they communicate to main memory over a channel, right? And so these 2 cores run different applications, and they'll start making requests to main memory. And so here the red core makes a request that goes to main memory, the blue core makes a request, and we see that these applications requests are actually interfering at the main memory because they're going through a single channel to get there. And so this inter-application interference is actually degrading system performance, right? And so this problem is further exacerbated by increasing the number of cores. So for example, in today's systems, we have GPUs with many cores and many different accelerators that have lots of different compute units. And the ratio of compute units to memory channels keeps increasing, right? So this becomes a bigger and bigger problem. Similarly, we have limited off-chip bandwidth. And so there's a single channel here, and we can try and make it wider by, we can have more bandwidth by increasing the clock frequency and so forth. But the number of pins in the channel is sort of limited by the physical design, and we can't increase that too much. So here's what it looks like in a more realistic system where we have multiple channels. So we have the same cores, the red core and the blue core, and now they're communicating with 2 different memory controllers, each of which has a channel to main memory. Right? And so there's some sort of interconnection network between the cores and the memory controllers. And in this example, it's a fully connected network, right? So what we have is that we have some sort of data mapping between the cores and the main memory. So for example, the red application here will map memory to both of these different memories, right, through both memory controllers. And each of these mappings is at the granularity of a virtual memory page. Similarly, the blue application will also map regions of memory, shown in blue here. And what we see is that this will cause interference between the different applications' requests, right? Because both applications are accessing both channels. If instead we do some sort of partitioning between these two different applications, let's say we give the first memory to the red application and the second memory to the blue application, we have some notion of performance isolation here, and the requests from each of the cores will go to different memory controllers. And this helps eliminate interference between the requests that these applications make. So I'm going to give a quick overview of the memory channel partitioning mechanism that this paper proposes. And so the goal of this mechanism is to eliminate harmful interference between different applications. And the basic idea of memory channel partitioning is to map the data of these badly interfering applications to separate memory channels, right? And it's based on two key principles. First, we want to separate applications that have high memory intensity and low memory intensity. And second, we want to separate applications that have high and low row buffer localities. So we can sort of picture memory channel partitioning having 5 key phases. So the first is a profiling phase in which we profile the applications that are running on the cores. Second, we use what we learned from the profiling phase to sort of classify these applications into different groups. Then we partition the memory channels available in the system into these different application groups. Then we assign a preferred channel to each of the different applications in the system. And finally, we allocate application pages to the preferred channel. And so in this 5-step process, the first step is done by the hardware. And so we actually make modifications in the memory controller to support collecting statistics about the metrics we're interested in. If you remember, the metrics are memory intensity and row buffer locality. The rest of the steps, 2 through 5, are actually done with the help of the system software. You can imagine there's some algorithm running, and eventually by the time we get to step 5, whenever the application makes a system call, requests new memory, the system software has to decide where to allocate that page, right? And so it can allocate it according to some policy specified by the memory channel partitioning mechanism. So memory channel partitioning operates over time in intervals, right? So here's a timeline axis. And so the first part is the current interval that we're running on. And we use that time to profile the applications, right? So as I said, we have modifications in the memory controller to measure both the memory intensity and the row buffer locality of the different applications. Then at the end of the interval, we do steps 2 through 4 with the help of the system software, and we sort of figure out, what the decisions we need to make and which applications fall into which groups. And finally, in the next interval, we enforce the channel preferences that we determined through steps 2 through 4, right? And so we repeat this process as the system runs. So we can actually take a step further and think about different ways to solve this problem, right? So the high-level goal of this paper is to mitigate inter-application interference, right? And so the approach taken is this memory channel partitioning mechanism. So the previous approaches to this problem sort of centered around memory request scheduling. And so they make the scheduling mechanisms aware of what the applications are doing and then try and schedule memory requests more intelligently. Note this is previous as per, before this paper was published, right? The approach that this paper takes is that they do the memory channel partitioning, so it's more of a data mapping approach. And it turns out these two approaches are somewhat orthogonal to each other. And so what you can actually do is combine both of these. And so the authors of this paper also propose a second mechanism called Integrated Memory Partitioning and Scheduling, or IMPS, which combines the benefits of these two different approaches, right? So we have data mapping and request scheduling all at once. So now we can talk about the hardware costs of each of these approaches, right? So the first mechanism is memory channel partitioning, and it's relatively simple because we simply need to add some support for profiling in the memory controller, and there's absolutely no changes to the memory scheduling logic at all. And so the changes in the memory controller, essentially we add a couple of counters, which are simply some registers, and then we have to have some storage to take care of the row buffer locality. And all in all, it's not that much storage relative to a big system. The second approach is the IMPS mechanism, and this requires all the same changes as memory channel partitioning, but also needs to change the scheduling logic a little bit. And so this is the hardware scheduler in the memory controller, and we essentially need to add 1 more bit per memory request. And what this means is that anywhere in the microarchitecture where we're storing the state of a request, we simply increase the size of that structure by 1 bit, which the authors evaluate this in their paper, and it's not super significant, especially relative to prior mechanisms which propose much more complicated changes to the scheduler, where you need to communicate information from the system software to the scheduler. That requires a lot more state to be added to the microarchitecture. So now I'm going to talk about some of the performance results that they present in the paper. And so here's a graph summarizing performance results averaged over all the workloads that these guys analyze. And so the y-axis shows normalized system performance relative to the baseline scheduling mechanism, which is this blue one, FRF-CFS. Right? And so we show results for 3 different previous scheduling mechanisms. So we have FRF-CFS, Atlas, and TCM, which are basically changes to the memory scheduling logic. and the two mechanisms proposed in this work, right? Memory channel partitioning and then integrated IMPS. And so what we're showing here is the relative performance results relative to FRF-CFS, right? And so what we see is that memory channel partitioning achieves a 7% performance benefit on average relative to the baseline mechanism. And using IMPS, we can push that up to 11%. And this shows that you can get significant performance improvement over the baseline mechanism, right? Now, if we look at the best previous mechanism, memory channel partitioning gives you a modest performance benefit, and IMPS does a little bit better with 5%. But the key takeaway here is that we actually managed to improve system performance by using these mechanisms, but at far lower hardware cost than the previous mechanisms need. So it's a net win. Okay. So one other thing we can analyze is the interaction of IMPS with different memory scheduling mechanisms. Right, so here we show, again, a similar graph. There's performance results on the y-axis, performance values on the y-axis, again normalized to the baseline FRF-CFS mechanism. And so IMPS integrates the MCP mechanism with modifications to a scheduling algorithm, right? And so here, what we're studying is if we make IMPS have different baseline scheduling mechanisms that get modified, right? And so the three mechanisms we're studying are FRF-CFS, Atlas, and TCM. So without IMPS, we see some sort of, some performance benefits relative to FRF-CFS. But as soon as we add IMPS, we see that the performance benefits are relatively significant, right? And so we see that IMPS actually improves performance no matter which baseline scheduling policy we start with and use to build IMPS on top of. Another takeaway from this plot is that we actually see higher performance improvement over the baseline FRF-CS mechanism relative to the other two. And this is because the way IMPS is presented in the paper, it's designed around FRF-CFS as the baseline, right? So we're adding this extra bit to the scheduling logic. This makes a lot of sense for FRF-CFS. And as you can see, it also makes sense for the other scheduling mechanisms, but it's optimized specifically for FRF-CFS. And you can read the paper for more details about all of this. So now I'm just going to give a quick summary of the technical content of the paper, right? So the problem they're trying to solve is that inter-application interference is significant and it affects system performance, right? And so to this end, the authors propose two new mechanisms for alleviating this interference. The first is memory channel partitioning, which tries to do some data mapping to separate the data of applications that will interfere with each other pretty badly, thereby eliminating that interference. The second mechanism is called IMPS, and this tries to prioritize low memory intensity applications during memory request scheduling, and that also reduces the interference, but at the scheduler level as opposed to data mapping, right? And so IMPS represents a combination of MCP and the scheduling changes. And what we find is that MCP and IMPS both actually provide better performance than application-aware memory request scheduling, which is all those other previous work schedulers that I showed. And it comes at much lower hardware cost, right? Okay, so that was a summary of the technical contents of the paper. I know Professor Mutlu presented it last time in great detail, so I wanted to get through that pretty quickly. And so hopefully it's all refreshed by now. So now I'm going to go into some of the analysis, right? So I'll first start out by talking about the strengths of this paper. And I actually quite like this paper, so I have 2 slides worth of strengths here. So the first strength I want to highlight is that memory channel partitioning and IMPS both represent novel solutions to a very important problem with multi-core systems. This memory interference problem I guess it's very fundamental to any sort of system where we have cores, different compute units that share memory resources, right? And as I was mentioning earlier, as the ratio of cores to memory channels keeps going up, this is a bigger and bigger problem, right? Because all of these things will want to access memory and they'll interfere and we'll have all sorts of performance problems. And this is one of the first few papers to tackle this problem I guess at a high level, right? Incorporating multiple different solutions rather than focusing on just one piece of it. Another strength is that MCP keeps the memory scheduling hardware very simple. And I try to emphasize that with MCP and IMPS, right? So MCP requires no changes whatsoever to the memory scheduling logic. And so in that sense, it's very simple to think about and implement, right? IMPS adds some minor changes to the scheduling logic, but compared with the prior proposals before this work, it's far simpler, and this is definitely a strength of the work. Another strength is that MCP and IMPS both enable hardware and software components to work cooperatively, but where each of them works best, right? So in the hardware component, we have some profiling going on in the memory controller, right? And so we're looking at both memory intensity and row buffer locality. And so this is at the request granularity, like the request going to memory. And it's quite hard for the system software to somehow get those metrics out of the hardware. And so what this paper does is it essentially comes up with a very easy way to expose this to the system software where it's best done, right? The memory controller itself can compute these metrics. And on the other hand, with the data mapping, it's very hard for the hardware to decide where data mapping is best, right? And try and migrate data automatically, things like this. That's something that's really well done by the application and the system software, because it actually knows what's happening with that data. And so the part about mapping pages to different channels is done by the system software here, right? So that's some changes to the operating system's memory allocation policies, things like this. And that's something that the operating system has a very good handle on and can do very well. And so this proposal combines both of those in a very neat manner. Another strength I'd like to highlight is that this, mechanism combines multiple interference reduction techniques. And so we talked about changes to the scheduler and then changes to the data allocation policies, right? And so these are two pretty different ways to approach the problem. And the authors actually find that these two work together better than each of these can work individually. And that's it's a very cool approach to the problem. So the next strength I want to talk about is that memory channel partitioning can also provide some sort of performance isolation between applications that are mapped to different memory channels. So performance isolation is the extreme case of reducing interference in memory, right? Because if we reduce interference, there's more fairness in the system. We're not contending as much for resources. But performance isolation is a very hard statement. It's saying that when I run this application, no other application will affect it, right? That's ideally what we want. And in general, that's a very hard problem to solve, right? People look at this for all sorts of reasons, right? Fairness when there's shared computing resources. For security benefits, so you don't accidentally leak information between processes. All of these are good reasons, right? And so it's worthwhile to think about that this paper is taking a step in that direction, right? By reducing interference, eventually we'll get to performance isolation, and so it's a step in that direction. And memory channel partitioning is also a very generalizable idea, because we're partitioning data at the granularity of memory channels, but it doesn't need to be that way necessarily, right? Channels sort of make sense at a first order, right? But we can also look at different levels of the memory hierarchy. So DRAM memory, for example, is broken into ranks after the channel granularity, and within ranks we have banks, and then we have substructures of different sizes. All of these are fair game for partitioning, right? And you get different trade-offs when you partition at smaller granularities, because now you don't need to, say, dedicate an entire channel for a particular application category. You can just dedicate a small number of banks, or say an application that doesn't require so many memory resources. You don't need to give it an entire channel to work with. You can give it just how much it needs. And there's a lot more dimensions to the trade-off space when you start partitioning at smaller granularities. And in fact, we'll see later on, I'll talk about some works that actually do extend this work to incorporate these different granularities and sort of describe the trade-offs there. Next, I'd like to mention that it's a very well-written paper. I think you'll notice this if you take a look at it, right? It's very easy to just see what the problem is the authors are trying to solve, the goals of the work, why the mechanism makes sense, like why it gets performance benefits. All of this is very clear and easy to get out of the paper, right? It's very accessible. And so, yeah, if you're interested in this work, I highly encourage you to take a look at it. It's very easy to get out the meat. And finally, the authors do a very good job with their simulation-based evaluation. They incorporate lots of different workloads. They do lots of sensitivity studies to different parameters in their design. They actually talk about a whole bunch of different aspects of their mechanism that I guess I didn't cover in the technical content here just for sake of time. And so that's a strength of the paper. Okay, so now I'm going to talk about some of the weaknesses I've identified in this work. So first I'd like to mention that the overhead of migrating pages between channels actually restricts the mechanism's benefit. So imagine the very first profiling phase that we do in the system, right? We turn the system on, we begin profiling the application. At this point, we actually have no idea what the application's characteristics are. And so when we're doing some page allocation to set up the application, we're making decisions based on something other than the metrics we're interested in here. And so once we do have some profiling information, we're going to have to go back and move that data around to where it actually belongs, right? Because then we can begin separating the applications into different categories and all of that stuff. And so for that first interval, there's a lot of page migration overhead that we actually have to suffer. And another case that the authors mention in the paper is that when we're actually running our application, let's say that we've partitioned them into separate groups and we've allocated a channel to application A. But if application A has a very big memory footprint, it might fill up the entire channel and require additional memory. And the problem now becomes, where do you allocate that memory from, right? Do you allocate it to something that's already allocated to some other process? Because then you'll begin having interference again, right? And so what you might want to do is figure out which memory is most commonly accessed and move it around such that you're reducing interference overall. And so all of that adds to the page migration overhead. And so the authors sort of take this into account in their evaluations, and they say that, this is a problem, and they find that in general, we don't have to do too much page migration. It's less than 20% of all the data in the system needs to be moved around, but it definitely eats away from the performance costs, and the authors acknowledge this. The next weakness I want to mention is that load imbalances can occur, where we have some memory-intense applications restricted to just a small part of the memory, right? So let's say application A is very memory-intensive and it's mapped to some channel, and some low-intensity applications mapped to a different channel. So now application A will start having issues potentially, right? Because there's limited channel bandwidth, and application is unable to take into account like all the channel level parallelism that would have otherwise existed. And so we can get some sort of load imbalance where one channel is super busy and another channel is hardly ever being used. And so in this case, we might actually want to introduce some interference, right, in order to balance the load a little more fairly. And so this actually gets a little bit complicated when we start trying to analyze this. And the authors mention that they can do this in principle, but it's a huge space, and it's very hard to identify exactly how much overhead this type of system has. The next thing is that, so this is a software-hardware cooperative solution, and while I do believe that's a strength because it solves problems at different levels of the stack where it makes sense, it's also a weakness because it makes this solution harder to adopt, right? So some designer who's designing the system now has to worry about making changes in their part of the design, but also have software support and be able to communicate this information back and forth, and it adds complexity, and therefore it's a weakness. The next thing is that the evaluation is solely done in simulation. And so this is sort of a trade-off by the authors, right? If they could try and implement this in a real system, but what would the real benefits be of doing that? They can convince you that their idea makes sense and it's reasonable based on simulation, then maybe that's where to focus efforts on. As you can imagine, right, so one of the weaknesses is that a software-hardware solution is kind of hard to adopt. It's also very hard to evaluate using a real system because the authors would have to make those exact changes, right? And so the authors here choose to do everything in simulation, and their simulation studies are very thorough and detailed. And so this is something that I've identified. The next thing I want to mention is that evaluation that the authors do, it doesn't actually consider multi-chip systems. So so the evaluation that these guys do, right? The diagram I showed at the beginning, we have some cores, we have some memory channels, and we try and partition data between them. However, if we think about a system today, we actually have a whole bunch more than that, right? We have some CPU with many cores accessing memory. We might have a graphics processor. We might have some image accelerators, various other chips on a device, and all of these will be contending for the same memory system, right? And so this leads to a whole bunch of different challenges that don't exist on the type of system that was evaluated here, because it's completely different types of workloads, and these aren't simply threads you can migrate between cores and things like this. So this is not evaluated in the author's evaluation. Finally, this is a question we can always ask for these types of works, right? Are these the best workloads to evaluate? It's a tough question because the authors here use a general benchmark suite, right? That's supposed to be representative of typical compute jobs. But if we know that this proposal is better for a specific type of system, maybe they should have done that, right? And focused on that system, the workloads that are important there. It's always a big question. And so that leads me into Professor Mutlu's favorite slide. And so these are the performance analysis rat holes again, right? And so I don't want to spend too much time talking about the workloads or anything like that because it probably won't be too fruitful a discussion. But it is worth mentioning in the weaknesses that this is something that you think is, I guess potentially a weakness. So next I want to talk about some limitations of this memory channel partitioning and the IMPS mechanisms. Right? So one limitation is that the mechanism might actually not be effective if the workload changes characteristics over time. Right? So let's say we have the first interval where we begin profiling, but in the next interval, if the application is doing something completely different, our profile is pretty much wrong. Right? It could lead us to make wrong decisions for actual runtime. And so we might end up doing completely the wrong thing. And then when we take the next profiling step, we'll find that the behavior's changed, and we actually need to move all this data around. We've made all the bad decisions, And so it gets very complicated when workloads aren't very uniform. I believe this is sort of an inherent limitation to this type of mechanism that's based on profiling, and then it does something based on the profile, right? And so if you're familiar with like concurrent programming, you get these types of issues, right, where you check whether some condition's satisfied, and then you operate on it, but if you haven't synchronized correctly, if something's changed, then what you're doing might be incorrect. And it's sort of the same principle here. The next limitation I want to mention is that if a system has a very small number of memory channels, memory channel partitioning has diminishing benefits, right? So in the worst case, you can imagine a system has only one channel. MCP can't really be applied, right? Because there's nothing to partition between. While that's typically not the case for modern systems, right? We have several channels. We still have many more compute units than we do have memory channels. And so partitioning is still limited in scope, right? And this is, again, a limitation of this kind of work, because if the resources aren't available, you can't do anything. Okay. So memory channel partitioning also adds restrictions on the physical to DRAM address mapping. And so this might not be obvious at first, but if you recall, this data mapping was done between channels at the virtual page granularity, right? So what happens is that we have to keep pages contiguous in memory, or at least make sure that a page maps entirely to one channel. But in today's systems, typically we stripe a page across all channels for performance benefits, right? So we can take advantage of all the channel level parallelism. And so if we're using memory channel partitioning, we can no longer do this. And so we have additional restrictions on how we can map data to main memory. And this is, again, a limitation of a system that uses memory channel partitioning. And we can't use those kind of optimizations if we have this type of system. Okay. So next, I'd like to talk about some of my thoughts and ideas based on the paper, mainly focused on extensions to the work, right? So the first extension I have is, can this idea be extended to different granularities in memory? And I know I mentioned this earlier in the strengths, that this is something that should be able to be done. And it's true. Some works have looked at this at the bank granularity, right? Partitioning between banks. But the memory system it's a rather complicated beast, right? We have many different types of memory potentially. And we have different granularities at which we can do this. We don't even need to limit ourselves to the hardware structures, right? If it makes sense to partition at some other granularity for some other reason, it's fair game. And so this work has a lot of potential follow-ups in terms of studying what are the right trade-offs for different types of systems. And another thing to note is that different types of memories actually, so not necessarily types, but let's say we have a DRAM system, right? But the DRAM that's used in a graphics processor is optimized for different constraints than the same DRAM used in a CPU, right? So in the graphics processor, we want very high bandwidth memory with lots of parallelism and things like this. Whereas in the CPU case, we're not necessarily concerned with the same trade-offs. And so the same idea can behave quite differently in two different systems, right? And so the authors of this work don't necessarily consider these other types of systems, but it's possible that memory channel partitioning is actually much better in a different scenario with a different type of system with different trade-offs. And so it's worth considering. Another potential extension is that can this potentially be used to provide full performance isolation? And with performance isolation comes performance predictability, right? Because if nobody is affecting your workload, then I can pretty much guess exactly how long my program will take to execute. And so again, like I mentioned earlier, this is a very strong constraint, right? Ideally, we'd have completely partitioned an application from another, but at that point, you pretty much have two different systems running these two different workloads, right? And so we're going to have some shared resources, and the idea is like, what can we really do to get this as far towards the performance isolation case as we can, right? And so we've already seen two potential solutions, right? One is to manage the scheduling policies more intelligently. Another one is to map data more intelligently. But there's a huge space of other potential solutions. And so this sort of leads me into my third extension that I wanted to talk about. And this is how can this memory channel partitioning potentially even be combined with other ways to do this sort of interference reduction? And so like I said, we've seen data mapping and we've seen scheduling. Maybe there's a third, a fourth way we can actually combine to make this into a much more wholesome solution, right? That comes much closer to the performance isolation ideal than these things individually can. And so here I've listed a couple of examples of different approaches for interference reduction. So the first one is what's called source throttling methods. And there's a couple of examples in the literature of these. And basically what this means is that we essentially punish applications which are hogging too many memory resources. Right? So if we notice that an application is dominating the memory channel bus or something like this, we can actually, at the memory controller, slow down this application, right? Not satisfy its requests as frequently as it really wants to. And this brings fairness back to other applications, but it also provides some measure of interference reduction, right? Because if there's a low memory intensity workload running alongside this beast, then that one won't suffer as much if we throttle the one that's asking for a lot of memory. And yeah, one example is this paper in ASPLOS 2010, which does exactly what I described at the thread granularity. Another type of, I guess another category of solution for interference reduction is the thread scheduling methods. And as you can imagine, this has no hardware changes whatsoever, right? In the operating system scheduler logic, we can simply decide that, oh, these two applications have characteristics that work well with each other. And so we should always try and schedule them at the same time because we know they're not going to interfere with each other. On the other hand, we could potentially have workloads that we know are going to interfere badly, and we want to make sure to never schedule them simultaneously, right? And so we can actually do this. Again, this leads to fairness benefits, performance improvements, all this good stuff. And so these are just two examples of different ways we can reduce interference, but there's, it's limited only by your imagination, basically. Okay. And finally, again, this is another question we can always ask. Can we evaluate this using a real system? And if so, how? And so it's a little bit vague to ask this question, right? But it has strong implications, right? Because when we evaluate something in simulation, we're making a lot of assumptions about other things that are hard to model. Whereas on the real system, we might see that there's completely different characteristics. We might find that certain cases that we expected to perform well actually perform terribly, or even vice versa, right? And so it's always a good question to ask, and potentially worth doing the analysis if it seems like this is the right direction to go. Okay. So this is one work I mentioned that sort of follows up on this memory channel partitioning idea. And this one uses source throttling. And yeah, as I mentioned, this is where we slow down applications that are asking for too much memory relative to other applications that are not, right? Here's a paper that deals with bank partitioning. And so this is essentially memory channel partitioning at a finer granularity. And they have several different mechanisms, and there's different trade-offs with bank level partitioning because multiple banks are within the same channel, right? And so they're not completely independent of each other because a request can still block a request to another bank if there's contention on the memory channel and things like this. But it's another idea that's been worth exploring. And so these guys did so in 2010. In 2012, yeah, in PAC 2012. And then I have one more paper to show, which again is also in 2012, but in a different conference. And this paper also looks at bank partitioning, but their implementation and their mechanisms a little bit different than the previous one. And so there have been sort of works that follow up on this idea and recognize that it is extensible and that there's potentially benefits from looking at it in more detail. So finally, I want to quickly summarize some of the things that I think are good takeaways from this work. So first, it's a novel method to reduce memory interference. That's always good. And I think in particular, the previous works before this one had been just looking at the scheduling policies, right? And so this one thought to look at data mapping as well and combine the two. And so this is a very interesting approach. In that sense, it's very simple and effective too because it's very intuitive, right? To understand that, we're separating data, so the applications won't contend as much. Makes sense. And so, yeah, I believe that's a very important part of the paper. Again, it's hardware-software cooperative, which ties back to the part I talked about before, right? Where it's sort of taking into account more than just one piece of the puzzle. There's also very good potential for work to build on it, right? So we talked about different structures, meaning at different levels of the hierarchy. There's even different metrics we can look at, right? Because this paper looks at memory intensity and row buffer locality, but those are by no means the only metrics that we can study, right? And yeah, as I said, multiple works have already built upon this paper. And finally, it's a very easy to read and it's a very accessible paper. So you can go take a look at it if you're interested. Okay, so now I'd like to give the open discussion. And so this is where I'd like to involve you guys in this discussion, right? And so here we have the sort of discussion starters that you saw earlier when Professor Mutlu presented the row clone paper. And they sort of apply here. And in particular, given all of the ideas I mentioned and the strengths and weaknesses, I think, so I think this is good brainstorming material for us to ask these questions. So first of all, what are your thoughts on all these previous ideas I talked about, and how practical is this mechanism? Do you think? Do you feel there's something else that we haven't already talked about? Yeah, so I'd like to open those questions up to you guys. Does anybody have anything to say? Yeah,
I think
go.
it's certainly more practical than other solutions, as you mentioned. The changes required in hardware are less significant. So it's although again we also have to change software, but I think it's still easier to do, as it might be possible in existing systems. So, yeah.
That's fair. I mean, as a follow-up argument, I guess I could argue that having to make any changes in the hardware is already a big step, right? So how much difference is there really between making a small change than making a slightly more significant change? I don't know. Yeah, it's a very hard question to answer. Like, obviously, it's nice to not have to change too much, right? You can just go in, change a couple of, whatever, some easy parts of the design and just ship it out. That would be great. But yeah, so what's nice about here is that you make fewer changes, but it also gives you more benefits than the previous approaches. And so it's like kind of doubly nice, right? And another piece of that is that what you mentioned about applicable to current systems. So requiring any changes in the memory controller, for the most part, makes it inapplicable, right? Because let's say the memory controllers, at least these days, are typically like hardware blocks inside the CPU, right? So if I wanted to implement this, say, on my laptop CPU, there's no way for me to go in and like modify the CPU, right, to make these memory controller changes. So unless the memory controller is already there in some programmable fashion, it's sort of a toss-up to say whether this applies. I mean, one part where it definitely does is the hardware changes here, they simply facilitate profiling, right? If you remember those 5 steps from before, only the profiling is really a hardware solution. And so if the memory controller has the ability to profile these metrics in some other way, like, a lot of processors these days have performance counters, right? And these performance counters can be rather comprehensive in some cases. And so maybe the memory channel partitioning mechanism can actually read the existing performance counters rather than applying the proposed changes that they propose in this work, right? So I think that's one way that maybe we can apply this to today's system, assuming those performance counters are already there, right? And yeah, those are good statements about practicality. Yeah. So, I don't know, any other thoughts? Fair enough, yeah. So the next question then is, like, will this problem become bigger and more important over time? So I know I mentioned a couple of times that, we have more cores, more compute units and all of that. So do you believe that actually will make this specific problem worse? Right? Just because I have more cores doesn't necessarily mean that I'll have more interference, right? It depends what I'm doing with them. So do you guys have any thoughts on that? Yeah, go for it.
The programs will get more resource intensive, so I guess it will be worse.
Why do you say more resource intensive? Like, how do you mean?
If you want to take some parts of today's application that compared to 10 years before that, they have, I think, far more data to transfer, right? So
right.
It is acceptable to expect the same difference in the next years, right?
Fair enough. Yeah, that's a very good point. So you're anticipating like changes in the workload characteristics as we go forward. Yeah. Sorry, go ahead.
It also really depends if the number of memory channels grows with the number of cores, or if one grows more than the other. Then, like, if memory channels grow more than cores, then we're fine. Not fine, but like,
it's not as big an issue.
We certainly have more channels to choose from.
Right.
And the second is, how are these cores used? You can either have multiple different jobs running on different cores, or you can distribute one task from the same program and do shared memory computing. So in the shared memory computing, we wouldn't really benefit from this solution, I think, as well. Memory is shared, so we cannot really partition. We can multiplex it maybe, but then we have synchronization issues. Sorry. Not synchronization.
Yeah, you're right, and just in general concurrency issues, right?
No, I don't mean concurrency.
Okay.
Coherency. Coherent, because we have.
Fair enough. Yeah, that could very well be the case. So I think, yeah, you're pointing out the shared memory is very interesting, right? Because a lot of, for example, let's say like data center, like database type workloads, they do this, right? They have a big piece of data they want to operate on, and they're trying to find a lot of ways to figure out how to operate on it with lots and lots of different threads. And they even have partitioning solutions, right? Like they'll partition this big piece of data into small pieces that each thread can work on individually, and then you avoid some of these concurrency issues. I don't know, it's sort of reminiscent of this idea too, right? Like here we're separating different applications, but one way or another you're partitioning things so they don't interfere with each other. In one case you have concurrency issues, the other one, I guess it's performance issues right here. Yeah, that's a very good point. Fair enough. Yeah, so I guess, yeah, so this is a very general question. Are other solutions better, right? So, yeah, so we talked about before, there were a lot of solutions which were just based on just the scheduling policy, right? And so the benefit there is that the hardware is sort of automatically managing this for you, right? You don't have to sit here and decide that, oh, these are the right metrics for me to use by which to partition my data. And you don't need to hope that, the system designer will implement solutions to read this correctly, partition the data correctly, not have any issues in that implementation. There is definitely the benefit of just the programmer being able to do whatever they want, and then it just works, right? So, I mean, that's one ideal case, right? But yeah, so what do you guys think about that? Like, do you think it's better to have this full system type solution, or just this restricted solution that you don't have to worry about? Yeah, go for it.
I think it's nice also a software component because if you discover new ways to profile things, then you can still change it with fixed hardware.
Yeah.
Which is certainly nice.
Yeah, I think that's a great answer. Yeah, it's like because it's in the software, we can modify it relatively easily, right? But once it's baked into the hardware, like it's stuck. Yeah, when the next best thing comes, there's not much to do about it, right? At least in most cases. Yeah, that's fair. I think that's right. So I think I also want to mention earlier, I was mentioning that the software and hardware solutions that are part of this IMPS mechanism and the MCP, they sort of do their own things where they have more information, right? So the like OS page scheduling policy has more information about where these pages are and which applications they come from, whereas the memory controller knows about the requests and how many requests are coming per unit time. There's no real way for the software to be aware of that without having hardware support, right? So it seems like there are some things that are really just, you have more information to solve it, and so that's where you should be doing it. That's a potential argument too. Yeah, fair enough. And then finally, is this solution clearly advantageous in some cases? So again, it's very generally worded, but I think one thing you can read from this is that we have all these different solutions that have different trade-offs. Like, is there one or maybe a few use cases you see where this type of mechanism is like the best type of mechanism to be using, or at least a very good fit relative to other ones? Because we said here that, for example, like we have to make changes at different parts of the machine, right? And so can you think of a system where all these different parts of the machine are owned by the same people, designed by the same people? Like if there is such a system, right, this could be a good fit, because there they can ask for the hardware changes, they can do the software changes, do it all themselves, and then ship you a product that just has higher performance. Sounds fantastic. Yeah, so whereas, right, as an end user of just a generic like desktop machine, say I'm going to go install whatever software I want, and I can't guarantee it'll have support, right? So, yeah, I don't know. Can you guys think of anything like this? Yeah, I think one example that comes to mind, at least for me, is so let's say in data centers or in like high performance computing centers, you basically have computing as a service, right? And so the administrators who are setting up the systems, they basically control everything, right? They can be like, I'm going to buy this specific CPU, I'm going to install this specific software, I'm basically designing the system how I want it, and the user doesn't really get the choice of, oh, I don't like your operating system. Like you submit jobs, they get executed, you use a virtual machine, whatever you need to. But this part of the stack is sort of owned by them, right? And so they can design it how they want. Like another potential example is, I guess, like, a lot of smartphones and things these days, especially like, like Apple devices, for example, right? You don't get the choice to modify like kernel operation, and the hardware is sort of designed somewhat in-house, and so they can potentially make these kind of changes. An Android system, if you install a specific kernel, you could have these optimizations there. And as long as the hardware supports it, it works, right? Yeah, so I think there's a case to think about, right? Like, where is this the right solution for, and where is it really not appropriate? Because in the general purpose device, like, I keep referencing laptops, but laptop, desktop, whatever, like, it might be better to just have a hardware-only solution where I, as the end user, don't really need to worry about it. So, yeah. I think, so that concludes this first example review. And I'm going to give one more after the break, and so I think we should take like a 10-minute break right now. Yeah, sounds good.